And share the screen. Okay, so I'm going to finish up 5.3 and start some of 5.4. We have plenty of time for preparing for the test for this week. So next test is this coming Friday, the 20th. Okay, then after that, we're down to just one chapter left. We only have 4 weeks left. And next week's a short week because we have Thanksgiving. So the semester is winding down fairly rapidly, as you can tell. So I'm going to introduce some of 5.4 even today. And then our last chapter, chapter 6, we're not even doing the entire chapter. Looks like just 4 sections. Okay, so overall picture, so 4 weeks left. Next week is short. So test 5 on Friday. And you know the spiel by now. You turn in this for homework, not that much. Okay, again, a 70% rule, turn in 70% at minimum of the homework, but you know, I end up doing a lot anyway. And then the last test will cover just this. Even with the Thanksgiving holiday, we should be able to finish in plenty of time. Okay, then our final exam is on Monday, the 14th. Okay, same thing via Zoom. I'll give you 2.5 hours. And please notice the starting time is 8:10, not 9:10. So 8:10 to 10:40. You don't have to turn in any homework, obviously, with that. You say, what do I do for the cheat sheets? Just keep all your previous cheat sheets. I hope you didn't throw them away, but if you did throw them away or you can't find them anymore, you can always make them up again. But if you have your, you know, your formula sheet for the first test and the second test and the third test and the fourth test, to just use them all. You don't have to reinvent the wheel, so to speak. Just keep them all for the final exam. Okay. And then that'll be about it. Okay. So we are here, and we don't have that much left. Okay. Again, for the benefit of those of you next semester taking 251, I am teaching 251, in fact, the same hour, 9 to 10 daily. I'll be conducting a class sort of the same. I might tweak a little bit how I do the quizzes, but for the most part, I'll be doing sort of like what I'm doing here. So that way, you know, if you like it, then go ahead and sign up. If you don't like it, then of course, you know, sign up for somebody else. I do think my class is already full, so there's a wait list for my 251 as I last checked. But anyway, we'll see how it goes. All right. Okay, let's see the quiz, which is now too late to submit. Okay, so e to the x. Now you need to give me some indication that e to the x and 2e to the x weren't the same graph. An easy way to do that is to just say this one goes through 0, 1, this one goes through 0, 2. Just make it a little bit higher. Or you could have indicated that on the same graph. So some of you put it in the same graph, say here's number 1 and number 3 is higher, which, you know, is a very logical way of doing that. Likewise for 2 and 4, number 2 goes through 0, negative 1. Number 4 goes through 0, negative 2. And you could have put them all in the same graph, as I said, or you could put 2 on one and 3 on the other, that's fine. And then number 5 was a shift 1 to the right and 2 up. So 0, 1 moves over to 1, comma, that should be a 3 actually, 1, comma, 3. Something like that. Okay, so I just needed something like that for the graphs. Okay, so that's the quiz. Okay, so I'm going to go back and try to finish 5.2. So I'll try to knock off the rest of that and maybe introduce one problem from 5.4, but even if I don't introduce any of 5.4, I still have plenty of time. Okay, so let's go back to 5.3. Okay, so solving these kind of problems again, and then I'll talk about the graphs. Okay, so I was going to show you 53. Okay, 2 times 3 to the negative x equals 2 times 3 to the x. Okay, first thing I'll do is get the 2's together, divide both sides by 2. 3 to the negative x. 2 to the 3x divided by 2 to the 1, I subtract 2 to the 3x minus 1. Okay, and now I should get this one. You have 3 to the negative x equals 2 to the 3x minus 1. How do I get those exponents down? ln. Okay, that's typically the trick. Okay, you have an exponent floating up here. So ln. Once you have the ln, this comes in front. This comes in front. See, I don't want the x's floating up there. I want them down. Right? So negative x ln 3 equals 3x minus 1 ln 2. Okay, distribute on the right-hand side. So 3x ln 2 minus ln 2 equals this. Okay, so how do I solve for x? Well, you got to get everything that has an x on the same side, and everything that does not have an x goes on the other side. So because of all the negatives, I decided to put all the x's on the right side, and everything that does not have an x goes on the left side. So this arrow means I added x ln 3, and this arrow means I add ln 2. So it looks like this. It looks a little bit nicer just because there aren't as many negatives, right? I don't like negatives, I like positives. So this one stays. This one, if I add it to the right side, becomes a positive. And if I add that, it becomes positive. So everything's positive now. Okay, so all the x's are on the right-hand side. The non-x's are on the left side. Okay, so you factor out the x parentheses 3 ln 2 plus ln 3. Divide both sides by 3 ln 2 plus ln 3. Okay, so this is considered the exact answer. And then a decimal approximation, if you want to punch it in your calculator, it's fine. Okay, like this, 0.2181. You might have to put extra parentheses. And again, some of your calculators, when you hit the ln, it automatically gives you a left paren. Then you have to close it every time with a right paren. Okay, so you have extra parentheses here and here. Okay, so the problem's finished. Maybe just for fun, let me show you what I would do. Okay, so yeah, and even if you're going to do it all at one time, even this should have parentheses. Maybe I should put extra parentheses here, like that. So parentheses, ln, parentheses 2. Okay, so this is going to be my numerator. Parentheses, parentheses, ln, parentheses 2, like that. Actually, I should have, let's see, 1, 2, 3, 1. Yeah, that's a lot of parentheses, actually. Okay, so divided by parentheses 3 ln parentheses 2 plus ln parentheses 3 paren. Okay, so I typed it in like that. Okay, if you can't see it fast enough, you can always check the recording. 0.2181. Like that. But be generous with your parentheses to make sure you're not messed up with the order of operations and so forth. Okay. All right, so that's it for that one. And then the last part of this section was some graphs. So starting with 55, sketch the graph of each function, right? Okay. So a quick reminder of graphs in general. Okay, so the exponential function, f of x equals a to the x, where a is any base, goes to 0, 1. The inverse function, f inverse, it looks like f to the minus 1 of x in green. That's log base a of x, where a is greater than 1. So for our exponential and log functions, the base is always greater than 1. Okay, so whatever the a is, as long as it's the same a here, they are inverse functions of each other. So that means 2 to the x and log base 2 of x are inverse functions. 7 to the x, log base 7 of x. E to the x and log base e of x. We have a shortcut for log base e of x, ln. So ln means log base e. If you ever forget what the base is, just peek over here. Base is e. Okay, and we know that the exponential function goes through 0, 1. That means the log function has to go through 1, 0. And they are a reflection across the line y equals x from each other, right? So if you put a mirror at y equals x, then the green and the red are inverse or mirror images of each other. Okay, and then after that, we just do our normal translation rules. Okay, so I will now make the assumption that this is the standard log function. We know log functions generally look something like this. That's if the base is bigger than 1. A little bit more complicated if the base is less than 1, but still, we'll start off with this. Okay, so for something like 55, they don't want us to plot points, just do our translation. So log base 2 of x minus 3. It's in parentheses. So I take the basic log function, log base 2. The basic log functions all look like this. They all go through 1, 0. Okay, and now this just means shift 3 units to the right. Okay, so instead of 1, 0, I move over to 4, 0. And then the vertical asymptote used to be the x-axis, which has the equation y, the y-axis, which has the equation x equals 0. I just move it over 3 units. So the vertical asymptote becomes x equals 3. So here we go. Y equals log base 2 of x minus 3. Looks like that. All right. Then 59, I did a progression, sort of like the quiz that we had. Y equals 2 ln x plus 1 minus 3. Right? So for 59. So there's 3 things going on. I have a translation horizontally, a translation vertically, and multiplying by 2 also. All right, so here's what I did. I start with the ln x, goes through 1, 0. Looks like I translated 1 to the left, so it goes through the origin, 0, 0. All right, then I multiplied it by 2, which means these go up higher, but this goes lower. Okay, so in red is 2 ln x plus 1. Okay, so I just made it go higher and lower here. Still goes through the origin. And then minus 3 shoved the whole thing down 3 units. So instead of 0, 0, it's 0, negative 3. Okay, so it ends up going something like that. All right, so the usual rules. Okay, this translate again means move. If you hear me say translate, I thought translation was for languages. That's true, but there's also a dictionary definition of translate, which means to move. Okay, so translate for us means move. So this one is left and right. This case is 1 unit left, and this is 3 units down. So it goes something like that. Okay, then 61, y equals ln negative x. Aha. Do you remember what happens when I replace x by negative x? Hint maybe is this. We said before, because of ln x, you can only plug in positive quantities. But now it's negative x. Okay. And the thing behind my pen must be a positive quantity. It's a negative x. So if they give me negative x, what do I have to plug in so it ends up being positive? I can only plug in negatives. Okay. So before, you could only plug in positives. Now you can only plug in negatives. That's a reflection across the y-axis. Okay, so here's natural log of x. Looks like that, right? Okay, here's ln of negative x. So this is 1, 0. Can you guess what this point is? Which I didn't write, but I'll write it now. Negative 1, 0. Sure. Okay, it's a reflection across the y-axis. Okay, and notice when you plug in negative 1, put negative 1 here, right? You have ln of negative negative 1. That's ln of 1, which is 0. Okay, and yes, whereas in this case, we said you can only take a natural log of positive quantities. Okay, I think I showed you that before, but I'll show it to you again. So ln of 0, oops, sorry. Ln of 0 should be not defined. right, error domain. And likewise, if I try ln of a negative number, well, on my calculator, it actually gives me something. It gives me a complex number, right? That's at the form a plus bi. That's 0 plus pi I. But on some calculators, it should give you an error message. Okay, so this is the error message. Okay, matter of fact, if I got my other calculator, let's see where my other calculator is. Yeah, this one's less fancy. I think this one should give me the error message. So -1. So let me see what happens if I hit ln this time. Yeah, error. So there it is. That's the way it's supposed to be. Okay, so over here, I can only plug in positive quantities. Now with the negative x, I can only plug in negative quantities because I have to plug in a negative in order for the thing inside the parentheses to come out positive, right? It starts off with negative x. So if it starts off with negative x, I can only plug in negative stuff in order to make it positive. Okay, so now I cannot plug in 1, but I can plug in -1 because then you have -1. Likewise, I cannot plug in 5, but I can plug in -5 because then I'll have -5, which is +5. Okay, so that's that. Okay, 63, which I'm not showing you intentionally for the moment, but remember what happens when I have absolute value of ln x. Absolute value. I cannot have anything below the x-axis. I cannot have any negative values for y. Okay. So here's ln x. Okay. If the stuff behind my pen comes out to be positive, stays the same. The absolute value of a positive is a positive, it stays the same. So this part stays the same. 1 stays the same. If I plug in 1, ln of 1 is 0. Absolute value of 0 is 0. Okay. So for the absolute value graph, I claim this part's the same. But do you recall what happens to this part down here that was negative? It becomes positive. So this part here bounces over to here. So I get the mirror image. I get the reflection across the x-axis of this part. So here we are. Here's absolute value of ln x. So this part here stays the same. Okay. But this part here, pretend you put a mirror right here and it bounces up over like that. So here's absolute value of natural log of x. Okay. Okay, then I'm almost finished except for 65, which is a matching problem. So we'll get that out of the way. And then I'm ready to start 5.4, which is an exponential growth and decay. Okay, every now and then this thing wants to turn yellow on me. I don't know why, but anyway. Okay, and unfortunately, I can't show you all at the same time. Hopefully you have the text. If you have the text with you, you can just look at it. But in my case, I have to keep bouncing back and forth. All right, so match each of these. Oh, ln negative x. We just did that one, right? So maybe that's an easy one to knock off. So which one is C? Closest one looks like this one, right? So C should be Roman numeral 1. ln negative x, we just did that one. Okay, then what about the other ones? B and D look very similar, right? Except this has a 2. Maybe we should try to knock this one off. Negative ln x plus 1. So B and D should still have the same general shape. Okay, so we know this one's out of the way. So that one and that one, that's the only oddball, right? Seems like. Negative ln x plus 1. Okay, so we know ln x looks sort of like this. The reflection across the x-axis would be negative ln x, and then moved up 1. Okay, so that should be Roman numeral 3. All right, so again, A should be Roman numeral 3. Okay, and then we just have to pick. Okay, B or D is either 2 or 4. B or D, 2 or 4. So how can we tell? It's a little bit tough to tell, but D should grow at a faster rate, or it's going up higher. So which one seems to be going higher? Or another way to do it is, well, think what happens when I plug in 2. If I plug in 2, and they show me what happens at 2, right? So I plug in 2, I'm taking ln of 1, which is 0, minus 1, which is negative 1. So one of them touches 2, negative 1. This one looks like it touches 2, negative 1. This one, let's see what happens here. If I plug in 2, taking ln 1, okay, so that, they both touch that. Okay, so that wouldn't really help. So both of them are good. Let's plug in a bigger number like, well, 3. If I plug in 3, these are both going to be ln 2, but this one's going to be higher. Okay, so which one's higher at x equals 3? 1, 2, 3, that's there. 1, 2, 3, it's already up to here. Okay, so number 2 should be D. This one's higher. 2 should be D. So by elimination, B should be 4. Is that right? Okay, so that pretty much does it. Okay, let's see if I can review that. But the answer's in the back of the book for those of you with the book again. Okay, so we agreed C was 1. We just did that one, right? Okay, C is 1. And then A was 3. And then we said this one was higher. It went up higher, so 2 should be D. 2 should be D. And that leaves 4 to be letter B. And that's about it. All right, so that's about it. I'm going to start some of 5.4, but not that much. Okay, so 5.4, the topic is exponential growth and decay. Page 304, exponential growth and decay. Okay, now there's a standard formula, but it's not always written the same way. Okay. On page 305, Q of t equals Q0 e to the kt. If you want to put this on your formula sheet, you may. Okay, I'll just say the Q's could change. It might be A, it might be N, it could be a whole bunch of stuff. So you have to be prepared for all of them, but they all really mean the same thing. This is for exponential growth. Okay, for K bigger than 0, it's exponential growth. If K is less than 0, then it's an exponential decay. It'll go down as time goes by. K is sometimes called the constant of proportionality. So a lot of real life situations, you'll either have exponential growth or exponential decay. Once in a while, you might hear somebody say something in the news that blah, blah, blah is growing exponentially or decaying exponentially. You say, what are they talking about? Okay, it means it fits this kind of pattern. Q of t equals Q0 e to the kt. I will give you my version, which unfortunately uses different letters, but I want to show you that you want to get comfortable with whatever letters. Okay, I've got my form having A. I'll show that to you in a second. Okay, so this section is all word problems, unfortunately. Okay. Essentially, you're taking all these words and trying to put them into here. Okay. So in a growth case, it looks like this. In the decay case, it looks like this. So exponential decay, graph is falling. Exponential growth, graph is rising. Oh, and you can see the author also even switches the Q's to A. So instead of Q, it might be A. A of t is A0, e to the kt or it or whatever. Okay, so I'm going to quickly show you my version of it. Okay. Now, if you want to use the book's form on your cheat sheet, that's fine. If you want to use my version, it's equivalent. Okay, A of t equals A0 e to the kt, and I'll tell you what all these things mean. So this is exponential growth and decay. Okay. A stands for amount. Okay. YQ, Q for quantity. You'll sometimes see P for population, N for number, and say, yeah, all these, they look different, but they're really the same. So this could be Q, Q, N, N for number, Q for quantity, A for amount, P for population. It's all the same thing. Okay, so I'll start off with A of t is equal to A0 e to the kt. Okay. A0 is the initial amount, the amount that you start off the experiment with. Okay, initial amount. Or you might say the amount at time 0. By the way, what happens when you plug in 0? You have e to the 0, which is 1. 1 times A0 is A0, which means the beginning of the experiment, the amount that you have is A0. Makes sense. Sometimes we say A sub 0. Okay. And again, be ready for this to be a P for population, or Q for quantity, or N for number, but it's all the same thing. Okay. What is A of t? It's the amount after time t. Okay. So after so much time has gone by, 2 months, 5 years, 3 days, or whatever, there's going to be a new amount. It'll either be bigger if k is positive, or it'll be smaller if k is negative. Okay, t is time, as you might think, and whatever the units they give us. It might be years, days, minutes, seconds, etc. And k is a growth or decay constant that the book was talking about. Okay. If it's a growth, k will be positive. If it's a decay, k will be negative. Okay. If you want to put this entire stuff on your cheat sheet, you may. Okay, so A0, initial amount. A of t as a function, A parentheses t, that's the amount after time t. T is given in time. They'll tell you the time. Years, minutes, seconds, days, whatever. K is a constant that we normally have to figure out, unless they happen to tell you in the problem. All right. Okay, so I'm just going to work through one problem for you, number 2, and then that was going to be it. 9:40 right now. Okay, so I was only going to do one problem, but it would take me a while to develop the one problem. Okay, so we have 9 through 16 all. Again, not odd, but all. So I was going to try to show you as many evens as possible because you don't have the evens in the back of the book. And I'll leave you to try to figure out the odds. Okay, so 5.4, number 2, page 310. Under ideal conditions, a cell of the bacteria E. coli, Escherichia coli, you've heard of E. coli perhaps, commonly found in the human intestine, divides to create 2 cells in approximately 22 minutes. Okay. So 1 cell becomes 2 in 22 minutes. It's doubling time, so to speak. Assume the initial population is 200 cells. Okay, so let's put all the data down. A0 is 200. 1 becomes 2 in 22 minutes. It doubles in 22 minutes, right? So that means after 22 minutes, the population doubles, or 400. Okay, think of it, if 1 becomes 2, it's as if to say you run the experiment 200 times, right? You have 1 E. coli by itself, it'll become 2. Well, you have another one, it becomes 2, another one. So that means if you have 200 at the beginning, it becomes 400 after 22 minutes. All right, so it asks us all this stuff. Find an expression for the number of cells after t hours. Okay, we have to find a k. Find a number of cells that will be present after 10 hours. When will the population reach 10,000 cells? The first thing we want to do is come up with this equation. Okay, because once we have the equation, then we're good. Okay, so the initial amount is 200. 200 goes there. Okay. Now, after 22 minutes, so I plug in 22 here, 400 here. How do I get 400? Again, 1 becomes 2 in 22 minutes. That means the amount doubles. Okay, so imagine you have this experiment that you're running 200 times. All 200 of them will double. All 1 will become 2, which means you have 400 of them after 22 minutes. So 400 goes here. That's the new amount. Okay, again, initial amount, 200. I'm using this formula. 200 goes here. 400 goes here. 22 minutes goes here. Normally, you don't write the 22 minutes. You know that the answer is going to involve minutes. Okay, so 22 goes up here. 200, 400. Okay. Solve for k. Divide both sides by 200. 400 divided by 200 is 2. So 2 equals e to the 22k. How do we get rid of e? ln, natural log both sides. Okay, so ln2, ln e to the 22k, these cancel out. So ln2 equals 22k. Divide both sides by 22. K is natural log of 2 divided by 22. Okay, that's approximately 0.0315. That's considered the growth constant. Okay, so try that and calculate ln2 divided by 22. 0.031506, blah, 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 blah. I'll just say 0.0315 for now. You actually want to keep as many digits as possible, but you probably don't want to write every single digit here. So I think 4 digits is fine, 0.0315. Okay, and a quick reminder, some of you have a calculator where when you hit ln, mine doesn't, but some of you, when you hit the ln, it automatically shows up with the left parenthesis. So for you folks, you have to close it with the right parenthesis like that before dividing by 22. Okay, and again, for some of you who have just a regular standard scientific calculator, you have to go backwards. So you folks, if you want to do ln2, you have to do 2 first. So I'm going to hit 2 and then hit ln. There it is. And then I'm supposed to divide by 22. The rest is the same. So divided by 22 equals, there it is, 0.0315, blah, 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 blah. Okay. So now my equation becomes A of t is 200 e to the 0.0315 t. Okay, and everything's in minutes. This is the equation, so that's the answer to part A. Find an expression for the number of cells after t hours. Once I have that, I can answer any other question that I want. B and C. It's just plug in. Okay, B. Find the number of cells that will be present after 10 hours. I just plug in 10. Oh, you know what? I think I messed up. Yeah, I'm going to change the problem to 10 minutes. They shouldn't have done that. They got it here in minutes, but they changed this to hours. Okay, I'm going to change everything to minutes. Okay, sorry. So it won't match what it says in the back of the book. Okay, so I'm going to make this all minutes. So that's minutes. Everything's in minutes. I don't know why they change units like that on me. Okay, that's a mean trick. Okay, so I'm going to do it in terms of minutes. Yeah, all minutes. So now I plug in 10. So A of 10 is 200 e to the 0.0315 times 10, which is 200 e to the 0.315. Okay, rounded to the nearest, that whole bacteria is 206. Okay, for bacteria, people don't leave your answer as a fraction. You want to the nearest whole number. Okay, so 206 if you punch it in the calculator. 206. So what am I talking about? There's no back of the book anyway. So, oh well, be that as it may. C, when will the population reach 10,000 cells? And by the way, this was going to be it for today. I was just going to do this and then we're done. But I just wanted to whet your appetite, so to speak, show you what we're headed for. I have plenty of time, hopefully tomorrow and Wednesday, to show you how to do the rest of these. I just wanted to show you one minimum. Okay, so as soon as I finish this, I'll be done, unless anybody has any question after that. We'll be done in a few minutes. Okay, so the new population is 10,000 cells. I plugged that in to the left-hand side for A of t. Okay, so 10,000 goes here, the left-hand side. So 10,000 equals 200 e to the k t. I already found the k, it's 0.0315. 10,000 equals the initial amount, 200 e to the k t. Divide by 200. 10,000 divided by 200 is 50. 50 equals e to the 0.0315 t. Get rid of the e with a natural log. Same thing. Naturally occurring logarithm, so to speak. So that cancels out. ln 50 is 0.0315 t. Divide by 0.0315. Okay, punch in your calculator, and we're done. Okay, I'll show you this for those of you with just a regular scientific calculator. You have to hit 50 first, 50 and then ln, and then divided by whatever, 0.0315. Divide 0.0315 equals about 124 minutes. Okay, but if it's like that, we usually change it to hours, right? So 60 minutes an hour, 2 hours and 4 minutes, so a little bit over 2 hours. Okay, so after a little bit more than 2 hours, there'll be 10,000 E. coli. Okay, so that's how to do that one problem. All right, so that's what we're up against in the next couple of days, exponential growth in decay. Taking all these words, okay, try to get them into the formula A of t, oops, you can't see it, A of t equals A0 e to the kt, and then go from there. Okay, so all of these are word problems, okay, and they'll be treated in a similar fashion. Okay. All right, so that's it for now. Close this, check the chat. The question was about the final exam. How many questions are on the final exam? I'm not sure. I usually give you about 10. So I'm leaning toward, I don't know, 15, 20, something like that is my guess for the final exam for now. Okay. All right, anybody with a question? Otherwise, we're done for the day, folks. Anybody else? Something? Okay, so I've shown you how to do one. Try to get started, but we'll try to do more of these tomorrow and Wednesday in preparation for Friday's test. All right, that'll do it for today, folks. Okay, have a good day. Bye, everyone. See you next time. Bye.